Differentiation, at least at this level, is about finding the gradient at any point on a curve. But what do we mean by the gradient of a curve? Because if you look at a curve, and we've got a curve here in this diagram, the gradient is changing all the time. So what do we actually mean by the gradient of a curve? Well, what we do is define the gradient of a curve to be the gradient of the tangent to the curve at any point. So if, for example, we look at the point A here, there's the point A, and this is the tangent to the curve at A. If we work out the gradient of this tangent, then we consider that to be the gradient of the curve at that point. And when we go to B, we would consider it to be the gradient of this. This looks horizontal, so the gradient there would be 0. Those are important points, just like D as well. So the gradient changes all the way along the curve, but it's going to be equal to the tangent to the curve at that point. Now, in later courses, you'll certainly be shown how to find the gradient at any point on a given curve from what we call first principles. And that really explains how we do it, the methodology. But we don't have time in this course to deal with that. So what we need to do is look at some different families of functions and how they differentiate. And the first one we're going to look at is just sort of a polynomial function, a power function of x. So in this expression y equals ax to the n, x is obviously x, and a and n would be numbers, such as we might have 3x to the power 4 or something like that. So in this case a would be 3, n would be 4. When you find the gradient function of that, which we call dy dx, then that becomes nax to the n minus 1. Now, the easy way to remember this is you've got ax to the n, so the n comes down in front and multiplies the a, so that's the n times a, and then you reduce the power up here by 1. So if you just remember that rather than remembering the formula, you'll be fine. There's alternative notations. If you call the function f of x instead, then when you differentiate, you get this f dashed of x. And the reason that there are different notations is historical, and I'll talk about that briefly in class. So let's go to the first example. Now, we want dy dx. So the 7 comes down in front and multiplies, and then we reduce the power by 1. Same thing here, dy dx. The 5 comes down in front and multiplies the 4, so that's 20, and we reduce the power by 1. Now when we have 7x, remember that's 7x to the power 1. So the 1 comes down in front and multiplies, which gives us 7x, and reduce the power by 1, which is 0. But of course, x to the 0 is just 1. So that's just 7. Now that makes sense because y equals 7x we know is a straight line, and the gradient all the way along it is 7. So it would make sense that the gradient function is 7. Now there's a couple of different ways of thinking about this one. So first of all, you could think of it as 5x to the 0. So when you differentiate, 0 comes down in front and multiplies, and of course anything multiplied by 0 is 0. But if you think about y equals 5, it's a horizontal line, the gradient of which is 0. So once again, we'd expect the gradient function to be 0.